All right, so this is the last video of the module. We're going to wrap up here with talking about the frequency limits of transformers. And really, this is just, similarly to the last point, which we were talking about the BH curve and saturation for transformers, which basically just applies to inductors because transformers are made out of inductors. This is relevant to transformers. The same goes for the frequency limits of the transformer. Because inductors have frequency limits, then transformers also have frequency limits as a result of the inductors ceasing to behave the way that they're supposed to behave or the way we think they are behaving above a particular frequency. Okay, so I'm going to talk about something here called parasitics. I haven't really talked about that much in this class, but basically parasitics are unwanted component values or unwanted effects from different things in our circuit. And so what we could say is, we could say that this wire, right, is ideal. And so the component, if we were to draw the component in an electrical schematic, it would just look like an inductor. But in reality, we know that there is some length associated with this wire, right? There's some cross-sectional area associated with this wire. And unless this is a superconducting material, we know there is some resistivity, even if it's copper, right? So we might say that even though this is a really good conductor, that it has, let's say 20 milliohms of resistance, then we can't neglect that in some cases. We have to actually take that into account. And so when we draw our inductor, this would be my inductor, and then sometimes you'll call this the equivalent series resistance, which we would have to put in series with the inductor if we were going to accurately model this inductor. Okay, so an ideal inductor, we assume that this is 0, but sometimes we can't assume that that's 0. That's called the equivalent series resistance because it's just the resistance of the wire and it's real, okay? And so there's also something called the, I don't know if it's called I don't think it's called the equivalent capacitance, but it's basically the it's called the inner winding capacitance that we would put in parallel with the inductor. And I'll call that CW for C winding. We know a capacitor is basically made of two conductors separated by some insulator, right? And so if we look at this, every single one of these is a conductor separated by some air, which is an insulator. And so if we distribute this for all the turns, there is parasitic capacitance between all of these windings and the next winding in the coil, right? So there's some lumped capacitance, CW, that we would have to model if we wanted to take this into account as a parasitic element. And so at a particular frequency, I'm basically getting into topics that are way too advanced for this class right now. But at a particular frequency, the inductor, which was originally just an ideal inductor and is actually something that looks more like this or better modeled like this, it stops behaving like an inductor because the capacitor basically becomes the path of least resistance. If you think about it, if I'm looking at a current flowing into this circuit right here, I have a current flowing in at low frequencies, right? At low frequencies, my capacitor isn't open, so the current's going to flow through the inductor, right? It's going to take the path of the inductor, and that's going to be the case for a very large number of frequencies. And then at some point, this entire time, the impedance of the inductor, right? The impedance of the inductor is j omega L, right? So as frequency is increasing, the impedance of my inductor is increasing as well. So that impedance of my inductor is going up. If I were to plot that against frequency, it's going up and up and up as I increase frequency. And at some point, this capacitance, right? That capacitance, which is a really large capacitance for small values of frequency, it is falling as frequency increases, right? So I've got my inductance, which is going up as frequency increases, and I've got my capacitance, which is going down as frequency increases. At some frequency, they meet, right? Some frequency, and then the capacitor becomes less impedance than the inductor. And so the trend for that current, it's going to follow the impedance here on the bottom. It's going to follow whatever is the lowest. And so at particular frequencies, this thing basically behaves like a capacitor. It will stop behaving like an inductor. And that's normally at a very high frequency. Usually it's in the 20 to 50 megahertz range, really high frequencies. So if you're doing things in the tens of kilohertz, the hundreds of kilohertz, you don't have to worry about this at all. It's really something you have to worry about at high frequencies, but it does exist. I'm just mentioning it as a frequency limit. And so I kind of show that in this plot here, that we know the impedance of an inductor increases, right, as the frequency increases. And that's exactly what they're showing here, right? You can see the impedance here in kilo ohms versus frequency. So this is just for an inductor. This is for a standard inductor. And because the inductor has some, you would assume, if you just plotted the frequency response of a single inductor's impedance in LT Spice, because it's ideal, you would just see this go up and up and up forever. It would never turn around and go down. The reason it goes down here is, like I said, there's a capacitance in parallel with it that's up here at low frequencies, and then at some point the two meet and the capacitor basically starts dominating the impedance. And this inductor is getting larger and larger in impedance, and that capacitance is getting smaller and smaller as we go to higher and higher frequencies. And so at this point, or I guess really from here and beyond, once this stops behaving linearly, we can basically say that this inductor no longer behaves like an inductor. And so from that point forward, the transformer is not going to behave the way that we think it should. Okay, you can probably get away with operating in this range, but to be safe, you might want to operate this below 100 megahertz. And yeah, that's basically the frequency limits of inductors, which applies directly to transformers. So if you ever are looking at an inductor data sheet, or you're looking for a transformer, and you want to know what frequencies it can operate at, look for something called SRF. That's called the self-resonant frequency. And that is going to tell you what frequency, basically what frequency the capacitor starts taking over the impedance, and at which you can no longer use that device as an inductor or as a transformer. Okay, so I'm going to go ahead and end this video here. That wraps up this module, and I hope that this was useful, and I hope you feel like you learned something in this module. And we'll move right on along into module 5 with the S-domain circuits and systems. So we'll see you guys in the next module.